Okay, so moving on, here's our discussion of gravitational potential energy. So gravitational potential energy is a relative quantity. So what that means is it matters where I set my zero. I need to pick a zero. Once you define gravitational potential energy zero, you can calculate the quantity of the potential energy. It's equal to the work needed to lift the mass to its current position from an arbitrary zero that you just identified. And the formula for that is mgh. So we consider both conservative and non-conservative forces. The gravitational force is a conservative force, meaning it does not depend on the path of the object. So recall from the previous page, when the object moves in this path, the work done by the gravitational force only depends on hf minus hi. It doesn't depend on the complete path of the object, not in the way that friction would. So because of that, we call friction or air resistance a non-conservative force, meaning it's going to do work the entire distance that the object moves, not just the component of distance that's in the direction of motion. Energy is easily transferred between conservative forces. Energy is less easily transferred when non-conservative forces are involved. Okay, the work-energy theorem states that there is an equation that relates the total amount of kinetic and potential energy to work. So here you see it, work equals delta K plus delta U, or the work done on a system will be equal to the change in the system's kinetic energy plus the change in the system's gravitational potential energy. The difference in energy from the initial state to the final state is equal to the amount of work done. Okay, the difference in energy from the initial state to the final state is equal to the amount of work done. And that's what we used in our bullseye lab in order to calculate the velocity. Okay, one of the consequences of this theorem is that if there are no non-conservative forces acting, then no mechanical energy is transferred in or out of the system, meaning if there's no friction or air resistance, then energy is conserved. Okay, so if you were to add up all the total energies at one point, you would see the same total energy at another point in motion if there are no non-conservative forces acting. Another way of saying that is to say that energy is conserved within the system, or to say that energy here equals energy there.